So I just finished marking for the test one, for the test, and I will upload the solution for the test to the e-learning. So I will let you know once I do that for the test, yeah, for the test solution. And then after that, I believe there is a letter for siapa mesej saya tu? Ira Wana. There is a letter. There is a letter for Henry. Okay, Henry, I have your letter regarding your KWSP. So I will bring the letter to you when I go to Penang. Okay, Henry?
Okay, sir.
All right. Okay, so today I will proceed. This is the planning. So by next week, we must finish the controller design in state space because we just have only about 4 to 5 weeks to cover all the syllabus. This is quite tight schedule because most of the Monday is a holiday, was holiday. So by next week we should finish the controller design, and we only have 2 weeks to cover the digital control, and another 2 weeks to cover the non-linear system. That's all. That's all that we can do. So for the lab number 2, I will give you the lab number 2 assignment on next week after you finish the lab 1 report or submit the lab 1 report. Okay, so for today, I will cover this topic, state space to transfer function. I believe I already upload this slide to the e-learning. And then I will go a little bit on pole placement controller design. Okay, so for the state space to transfer function, I will finish everything here today. Okay, so for the control design, I will go up to rules in order to implement the pole placement controller to the state space. All right. I believe I share the screen. All right. Okay. Yes, I share the screen. Okay, state space to transfer function. Pointer vision pen. Dr. Halim already teach you how to try to translate the state space into a few form, such as phase variable form, observable canonical form, cascade, and so on. Okay, so today I will proceed with in the previous topic, you learn about the state space structure, the PVF, OCF, and so on. And after that, you also do the modeling. Then state space to transfer function to state space, signal flow graph done, simulation on the model, this is done. So this is the thing that we need to cover. Okay. In this topic, the student will learn about the conversion between state space and transfer function, the analysis of the conversion system. Okay. If you still remember in control 1, you learn about the transfer function. Okay. And for this semester in control 2, you learn about the state space. Okay, so now actually the transfer function and state space can be related each other. Okay, you can connect, or you can you can convert. You can convert from transfer function to state space. You can convert, and also you can convert from the state space to the transfer function. So today we will focus on this area, state space to transfer function. Okay, so this is the control number one. Control number one, you learn about the time domain and frequency. Sorry, this is control two. In control two, you learn about the time domain, and this is the control one. You learn about the frequency domain. S refer to frequency, T refer to the time domain. Okay, so that's why we call frequency domain and time domain. All right, and then after that, in order for you to convert the state space to transfer function, convert state space to transfer function, you must use this formula. This is the formula that you need to use in order to convert from state space to transfer function. All right. So I believe this already covered by Dr. Halim on last week. This thing done. Okay. So now I will teach you how to use this formula in order to obtain this transfer function. Okay. Firstly, how the formula is obtained. Why need to use this formula? Why don't use the other formula? This is the proof why we need to use that formula. Okay, so you know that this is the state space equation. X dot equal to ax plus bu. And then after that, because we need to convert from time domain to frequency domain, so that's why you need to Laplace. You do the Laplace. The x dot t become sxs. Axt become axs. But become bus. Okay, so finally, you just rearrange until you get this equation lah. Xs equal to Si minus A equal to Bus. Why? Because our focus is to find the transfer function Ys divided by Rs, is it? This is the thing that we need to focus. So you have Xs. Okay, so the Xs, so you transfer Xs there. So that's why become Si minus A inverse B multiplied with the Us. And then the meaning of I is the identity matrix, S is in the frequency domain. So what is the meaning of the identity matrix? So let's say your system is second order system, your identity matrix will be 1, 0, 0, 1. Second order system. So let's say if your system is third order system, what will be your identity matrix? What do you think? There will be 3 by T because there is a third order system. This is second order system. Your identity matrix will be 2 by 2. The third order system, your identity matrix will be 3 by 3. So what do you think will be here? Look at this pattern. What do you think for the identity matrix?
0, 1, 0, and 0, 0, 1.
0, 1, 0. So you look at this pattern diagonal. The diagonal here, what is the value here? The
1
diagonal
and 1.
1. So it means that the diagonal here must be 1, 1, 1. The rest will be
0.
0. Yep. The rest will be 0. So this is the meaning of the identity matrix. Boleh? We have Dr. Halim here. Actually, I'm in Dr. Halim rooms. Okay, so we come like this lah. This is the identity matrix of the third order system. Okay, so I believe you can imagine what will happen for the identity matrix for the fourth order system lah. So the diagonal always become 1, the rest will become 0. Okay, proceed. Okay, so now we focus on the x dot equation and we Laplace them. and this is what happened. Now we focus on the output equation, and then we Laplace the output equation. So this is happen, ys equal to this one. So now we have two equations here, equation xs and equation to ys. Now I substitute this equation there, and you got ys c c xs is the this thing. This is the xs. So that's why I replace in here. Actually, this is represent the xs plus with dus. Okay, and then after that you can see the common value here is us, is it? Us and us. That's why I factorize the us, then become CSIA inverse b plus d, because the definition of the transfer function must be output divided by input. So that's why I move output and divide by input. So this is the transfer function lah. So that's why you must use this formula in order to obtain the transfer function from the state space. Okay, please always remember this thing. Yeah, this thing is really, 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 really important. How to prove, how to get the formula of the state space to transfer function. Okay, before I proceed to the next slide, anyone would like to ask anything? How is it?
So
So,
far, no question.
So far, okay.
does it
Mhm.
so what you mean is that this slide is basically uh,
Yes,
so
proceed.
what are we going to learn is basically how to like derive the state space to transfer function equation, is it?
Yes, that's the objective of this slide. Okay,
Okay, okay.
all right. Thank you. So I proceed to the next question. Okay, so this is the thing. I believe I already upload this slide to the e-learning, is it? Anyone would like to confirm it?
Let me check.
All right. Okay, so now the most crucial part. The most crucial part. Okay. The most crucial part.
Sir, not yet.
Once again.
The slide you say, is it in the e-learning, right? I checked, didn't have.
Okay, so I will upload lah. Sorry for that. Thank you for confirmation. Okay, so the most difficult part in this case, because this is in matrix, the most difficult part is here. This thing. This is, if you can do this, you can answer all the questions regarding to the state space to transfer function conversion. Okay, so Si minus A inverse. So what is the meaning of this? So that's why I already give you some example how to do the inverse matrix. Okay, the knowledge that you must have before can convert state space to transfer function. Firstly, you must know how to do an inverse matrix, and then you must familiar with matrix operation such as sum, subtract, multiply, and divide of the matrix. Okay, so this is, I show you example for the inverse for the two second order system. Actually, if you have numbers such like this, and 2, 1, 3, 4. Let's say I ask you to get the inverse. What is the A inverse? You can use calculator straight away. You can get the answer easy by using the calculator. Okay, because you have numbers 2, 1, 3, 4. Okay, you can use calculator. Similar to the third order system. So let's say I say that B, you have the number of 1, 5, 4, 2, 8, 1, 6, 2, 4. Okay. And then I ask you to find the B inverse. you can use calculator easy, okay, to get the value. But in according to the formula, the inverse is Si minus A. So it means that you need to do the inverse of, let's say, S plus 5, 2, 3, S. Do you can use a calculator to find the inverse matrix of C? C inverse equal to what? Do you can use it calculator in order to calculate the C inverse matrix? No, is it? Because you have S in here. So that's why you need to know how to do it manually. Okay, so that's why I give you example in this slide. Boleh buka pula dah. Okay. You just click the link. So this is how to do the second order inverse matrix. Okay. So I developed this technique. The technique that I developed is 3T and plus 2T technique. Okay. Because A inverse, the definition of A inverse, you need to find the A inverse, is adjoint A divided by determinant of A. Okay. To calculate the adjoint A, you need to know you need to use 3T technique. And to calculate the determinant of A, you can use the 2T technique. Okay, what is it 3T and 2T? Okay, 3T means transpose tutup tanda. Okay, 2T is tutup dan tanda. There's only the difference is adjoint you need to transpose, but for the determinant, you not need to do the transpose, okay? So firstly, I show you how to do the adjoint A. First T is transpose. So you need to transpose from 1 to the horizontal become vertical. Okay, the group of 1 here, 1, 2 become 1, 2. Horizontal, vertical. And 3, 5, the horizontal become vertical. Transpose. And after that, you need to tutup. The second T is tutup. Firstly, you need to tutup one by one. You tutup this first. If you tutup this first, and then you just cross all the horizontal and vertical, the only numbers left is 5. Okay, and then you tutup number 3 here. Number 3 here, and you tutup the whole horizontal and vertical, the left number is 2. Okay, and then you tutup number 2 here, go cross all the vertical horizontal, the left number only 3, and finally you tutup 5, the only numbers available only 1. Okay, transpose done, tutup done, and finally tanda. Okay, tanda. Since this is a second order system, this is the tanda pattern. You must remember this pattern: positive, negative, alternate. Positive, and then the rest will be alternate. Okay, since this is second order system, so you need just to take out only 2 by 2 from the top, and then this is the tutup result. Tutup result is 5, 2, 3, 1, and then you apply the tanda. 5 should be multiplied with the positive, 2 multiplied with the negative, 3 multiplied with the negative, 1 multiplied with the positive. So it become 5, negative 2, negative 3, and 1. So this is the result for the adjoint of A. Okay. Any question regarding to this one? Is it clear or unclear? So if unclear, please let me know which one before I proceed to the second page. Okay, I believe there is no question. All right. So to get the determinant of A, you just need to use 2T technique. you need to tutup and tanda. So before you tutup, you just need to choose only one row or column. You can choose any row or column that you like. In this case, I choose 1, 2 row, 1 and 2 row. Okay. So to calculate the determinant, I put the 1 and 2. Okay. So as usual, because I choose 1 and 2, I need to tutup 1 first. The rest number only 5. And then after that, I need to tutup 2. The only left number is 3. So what I need to do, 1, 1 here. The left number is 5, is it? So 1 you need multiply with the 5. And then you choose 2 here. After you tutup, you get 3, is it? 2 multiplied with the 3. Okay, done for tutup, and then you apply the tanda. Because you choose this column, okay, you choose this row, so you must remember this pattern. The pattern is positive and negative, because you choose this row, you must use the comparable row inside this pattern. So the first one is positive and second is negative. Finally, you get the determinant is -1. Okay, so now you already have the adjoint A and determinant A. The adjoint A result, this one, divided by the determinant A result is -1. So this is the A inverse that you obtain from the calculation. So the answer is, this is your A. So the A inverse, this is the answer for the A inverse. Okay, so similar, same thing with the third order system. Cancel. Similar with the third order system. You just need to apply the same rules. Okay. To calculate the adjoint, okay, so example, A, this is the A, and then you need to find the A inverse, and then you just need to use the adjoint formula divided by the determinant formula. Okay, so for the adjoint, you just need to use the 3T. Firstly, you need to transpose first. The row become column, and so on. And after that, you need to top, because there are 9 numbers, 3 by 3, 3 by 3 matrix, so there are 9 numbers, is it? So you need to do 9 times. 9 times of tutup. So you need to tutup the first one, the left is 1, 0, 1, 2. And then you need to do the second tutup, this thing, third, fourth, fifth, sixth, 7, 8, and 9. Okay, 9 tutup lah. So after you tutup, this is the result. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and after that, you need to calculate the value here, because this is in matrix, right? So you should get a value. So how to get this value? You need to remember this pattern. This is fish pattern. Start from here, go down diagonal, go up, and cross again. So here you have A. I name the point here. This is point A, point B, point C, and point D. Point A, point B, point C, point D. So you just remember this pattern, go down, up, and go down. Go down, out, and go down. So if you cross, you need to multiply A multiply with the C. Go up, you need to minus D multiplied with the B. So this why become AC minus DB. AC minus DB, AC minus DB. AC minus DB. Okay, so this is the pattern lah. Okay, so you apply this pattern and then you can get this value 1 multiplied with 2 minus 1 multiplied with 0, 0 multiplied with 2 minus 1 multiplied with 1, 0 multiplied with 0 minus 1 multiplied with 1, and so on. After you calculate everything, so you get this value you calculate. And then the third T is you need to apply the tanda because this is the 3 by 3 matrix. So you need to extract 3 by 3 sign pattern lah. And then you apply the sign into this after the close result. So positive, negative, positive, negative, positive, negative, positive, negative. And then this is the result for the adjoint of A. Okay, done for the adjoint A. Now solve for the determinant of A. The determinant of A, you just need to use the tutup and tanda. Alright. Okay, I would like to ask you to get the determinant of A, I can choose any row or column that I would like. Okay. So according to this statement, choose any row or column that you prefer. Why I choose 101 in here? Anyone would like to comment by reading the statement in 1? Why I choose 101 row?
Content as 0.
Okay. And then what is the another possible that I can choose? That easy for me to calculate.
102.
Row number 2,
Row number 2, which is
210.
210. So how about if I choose 112?
More complex multiplication.
Okay, still you can choose that. However, you need to calculate more. Okay, you can choose 112, but you need to calculate more. So it will take time in order to calculate the determinant of A. Okay, so firstly I choose 101. 101. Firstly, I need to close the first one. This is the answer. And then I choose the second, this is the answer, and I choose the third numbers, this is the answer. However, you can see that though if you close 1, you need to multiply with the thing. You close 0, 0 you need to multiply with this thing. You choose, and then after that, the final is 1, you need to multiply with this thing, is it? So if the row or column that I choose many of 0, so this thing I not need to calculate because anything multiplied with the 0 will become, anything will multiply with the 0 will become
0.
0. So I don't have to calculate this value. Okay. So that's why I choose the row or column that have many 0. So same thing, you just need to use the pattern 1 multiplied with 2 minus 0 multiplied with 1. And then 2 multiplied with 2, this one not need to calculate. 2 multiplied with 1 minus 1 multiplied with 1. So finally, this is the answer for the determinant. So the final answer here, this is the A inverse for the third order system. Okay. However, you can use calculator in order to calculate because everything here is the number. Okay, so why I choose or why I teach you how to use this technique, because let's see, continue with the slide. Let's continue with the slide. All right, so example, obtain the transfer function for the system below. Remember, if I have the state space, and then the question obtain the transfer function, so automatically I need to use this formula. Inverse B plus with D. Okay, so this is the formula to get the transfer function. So the first thing you need to know, this is A, this is B, this is C, and D equal to what? Here. D matrix equal to
0.
0. Okay, so there is no D matrix here. So firstly, what you need to do, use this formula. You need to calculate Si minus A first. Okay, you need to calculate Si minus A. Whatever the question is, you must calculate this thing first, Si minus A. This is really important for the next topic for the controller design. You must know about this. Then you can do the controller design for the state space. Okay, since A is 2 by 2 matrix, then the identity matrix will be like this lah. If if A matrix is 3 by 3, then this is the identity matrix. This is for the additional information. Okay, so what is your Si minus A will become? This is S, this is I, minus, this is the A matrix. Okay, so now S multiplied with I minus with the A matrix. So if S multiplied with I, this is the result, Si. This is the result for the Si, S multiplied with I. So S multiplied with 1 will become S. S multiplied with the 0 become 0. S multiplied with 0 become 0. S multiplied with 1 will become S. So you have Si matrix here. And then you need to multiply with the A matrix. S minus with 2 become S minus 2. 0 minus with negative 1 will become positive 1. 0 minus with 3 will become negative 3. And S minus with negative 4 become S plus 4. Now you already have Si minus A answer. This is the first thing that you need to do. And then after that, you need to obtain the Si minus A inverse. So the Si minus A inverse is a formula adjoint S minus A divided by determinant of Si minus A. So you know that this is your Si minus A. And then after that, you need to use the, you need to point option. Okay, you have Si minus A. And then you need to calculate the adjoint S minus A. So how you get this result? So what you need to do, you need to use the 3T technique. 3T techniques. Firstly, you need to transpose. So you have Si minus A here, you need to transpose it. Become S minus 2, 1, negative 3, S plus 4. This is for the first tutup. For the first T, that's mean the transpose. After that, you need to tutup. The second T is tutup. So it will become S plus 4 because you tutup S negative 2, minus 2. So you will have S plus 4. Eraser mana lah. S plus 4. If you tutup negative 3 here, the rest is 1. If you tutup 1 here, you tutup all the vertical or horizontal become negative 3. And then you tutup S plus 4 become S minus 2. The third T is standard. Since this is second order system, you need to apply this standard. Remember the pattern: positive, negative, negative, positive. So finally, your adjoint become S plus 4, negative 1, 3, and S minus 2. That's why you got this answer. Okay, by apply the 3T techniques. Okay, and then after that, you need to calculate the determinant S minus A. As usual, for the determinant, you need to use the 2T technique, tutup dan tanda. So you have your S minus A here, and then I choose the first column, the first row, so become S minus 2 and 1. And then after I S minus 2, I tutup S minus 2. The only number left is S plus 4. And then after that, I tutup number 1 here. The only number left is negative 3. And then remember the pattern. The pattern here is positive, negative, negative, positive. Okay, because I choose this row, so I need to use this pattern. So you apply the sign is positive and negative. So finally you get S square plus 2S minus 8 plus with 3, and this is the answer for the determinant Si minus A. Okay, so finally the Si minus A inverse, this is your adjoint and this is your determinant. So this is the answer for the Si minus A inverse. Please wait for a while. Keep. Hello. Waalaikumsalam. Okay. Mana lagi dah? Alright. We done this one done. Okay. So this is Si minus A. So now you already have this information. You have this information. So now you can calculate straight away the transfer function. So you have C matrix. The C matrix is 1, 0. B matrix is 1 minus negative 1. So you know that the C matrix is 1, 0. And then after that, the Si minus A, this is the answer. Okay, so you just put it there. S plus 4, negative 1, 3, S minus 2, and just S square plus 2S minus with 5. And then you just need multiply with the B, 1, negative 1, plus with the 0. So you can use this formula in order to calculate the transfer function. Okay, so this is the thing. So the final answer is the transfer function is S plus 5, S square plus 2S minus with 5. Okay, so in order to calculate this formula, you can take out this one because this one is not involved at all for the metric calculation. So you just need to calculate all the metrics first. So that's why in this note, I take out 1 over S square plus 2S minus 5. So you just need to focus on this. All right. So this is for the answer for this example. Okay, so this is the transfer function. So in conclusion, this is your state space after you apply this formula, and this is your transfer function. Okay, before we have about 5 minutes break, I want to ask you one thing. Based on this transfer function, based on this transfer function, what is the parameter that you need to refer in order to tell the system stability? Which one? You have GS here. You have S plus 5 there. Come in. Yeah. Kunci. Ambil. And then after that, you have S square plus 2S and minus 5. So which part that will tell you the system stable or unstable? You have part number, I name it as a A, this is B, and this is C. So which part will tell you the stability of the system? Any answer? A, B, or C? How you want to know the system stable or unstable? By looking at the transfer function.
B and C.
For the stability only. You have B and C. If you still remember, what is the thing? I give you a clue. Pointer option. If you still explain here. So how you want to know the system stable? What is the rules to make sure the system stable? Explain, you have pose, and then you have 0. The system only stable when? When what? You have pose, you have 0. So is it pose or 0 that will tell you the system stable or unstable? Which one?
Pose.
Pose, is it? So between B and C, which one will tell you the pose location? B or C? You have B, you have C. So which one will tell you the system pose location? Come on.
E.
B, okay? Because once again, B. This is the numerator. The numerator always tell the 0 location.
C.
Okay. And then the C will tell you the post location. Okay, post location. So it means that between B and C, C will tell you the system stable or unstable. So let's say if I ask you, how about the stability of this system? So you just need to look at the C equation, S square plus 2S minus 5 equal to 0, and then you need to factorize it and see, is it posed on the left hand side or posed on the right hand side? If the left hand side, stable. If one, at least one on the right hand side, the system become unstable. Okay, so this is what we call as the characteristic equation. Okay, this is the characteristic equation lah. So if I could say, characteristic equation determine the stability of the system because uh, the characteristic equation will tell you where is the post location. Okay. So if I give you one question here, is I give you one example lah, one question. Okay, I give you the state space. The question is evaluate the stability, the system stability. This is my question. I give you this state space, and my question is evaluate the system stability. Okay, so you know that to evaluate the system stability, you need to find the characteristic equation. Because the characteristic equation, you can know where is the post location. And then based on that, the characteristic equation only at the C part here. Okay, so according to this one, s squared plus 2s minus 5 you can see that s squared 2s minus 5, it coming from the determinant si minus a. Okay, so it means that the determinant si minus a will tell you the characteristic equation. The adjoint si minus a is not tell you this characteristic equation. Only the determinant si minus a will tell you the characteristic equation, will tell you the stability of the system. So, according to my new question, you not need to calculate everything. No need to tell the system stability. What you need to do, you just need to calculate the determinant Si minus A, and then based on the determinant Si minus A, you know that the post location at one pole at the 1.45 and the other pole is at negative 3.5. Hence, the system is unstable because there is a pole located at the right hand side of the S plane. So you don't need to calculate everything here. You just need to calculate the determinant Si minus A. That's all. If the question is something like this. Okay. So this is example number 2. We will take about 5 minutes breaks before proceed with this example. I think only 2 examples in this slide. And then you have exercise there. Okay, so we will continue at 4 for the second example. Alright, so I will continue with the lecture. Continue with the second example, how to calculate the transfer function from the third order state space. Okay, according to the question is, so this is the third order question, third order system. So the question is obtain the transfer function for the system below. Okay, so let's say I change the question, determine the stability of the system, what you need to calculate actually. If the question I change to determine the stability of the system, what you need to calculate, what is the parameter that you need to calculate? You can answer in the chat box, or you can answer straight away using your microphone.
The determinant.
Yes, you just need to calculate the determinant only. All right. However, the original question here, uh, you need to obtain the transfer function. So you need to use this formula. Okay, so you clear about how to solve it yet? All right, thank you for the answer. Okay, so as usual, what you need to do, you just need to obtain the Si minus A first. This is the step. Normally for the control system, you just need to remember or you need to follow the steps only. You need to know the procedure. You need to remember the procedure. If you know the procedure and you can do the mathematics, you can solve the question, including the controller, including this kind of the question. You can do it easily. Okay. So this is the procedure in order to obtain the transfer function from the state space. Firstly, you need to obtain the Si minus A as usual, because this is the 3 by 3 matrix, so the identity matrix will be like this. Okay, and after that you need to calculate Si minus A. So as usual, this is S and this is I minus with the A matrix. This is the answer. Okay, and then after that, after you obtain the Si minus A, so you need to calculate Si minus A inverse. So this is the formula, adjoint Si minus A divided by determinant Si minus A. So you know this is Si minus A, okay? And this is your adjoint Si minus A by using the 3T techniques. I give you, you can try do it by yourself by using the 3T techniques and follow the procedure example that I show in the link here. Okay, and then I hope you can get, I believe you can get this answer for the adjoint Si minus A. Okay, this is the Si minus A adjoint. And then after that, you need to calculate the determinant Si minus A by using the 2T techniques. Okay, 2T techniques. And then this is the answer for the determinant Si minus A. Okay, so thus the Si minus A inverse, this is the adjoint Si minus A, and this is the determinant Si minus A. So finally, you apply to this formula C Si minus A inverse B plus D. So this C, this is Si minus A inverse, this is B matrix plus with D. Okay, so you just in the calculation for the matrix. Okay, you just take it out, and then this is your C, and this is a adjoint as I'm going to say, and this is B. Okay, and then this is the final answer. Okay. So in conclusion, the state space, this is state of the state space, and then you want to convert to the transfer function, this is the answer by using this formula. Okay, all right. So as usual, the denominator part we call as a, so this is contributed by the determinant si minus a. This is a characteristic equation. Tak baca lah. Ha. Kita tak start habis lah. Bilik aku langsung tak ada internet. Jadi dia tak keluar. Kena left balik. Kena join balik. All right. Okay. Sorry for that. Okay. So, where is the last thing that I do you listen when I explain to on this slide for the exercises? Thank you.
I think before this slide.
Until this slide, all right.
No, I think before this.
Or before this. Okay. Thank you. I think on this slide, is it?
Yeah.
Okay. Thank you. Okay. Okay. So, I would like to mention you again. So, according to the question, this is a state space. And then after you apply this formula, and this is the transfer function. Okay. And then as usual, for you, in order for you to determine the stability of the system, you just need refer to the denominator part. So the denominator part is the characteristic equation. We call it as a characteristic equation. And this thing we just need to calculate the determinant Si minus A only. Alright. And then after that, based on this transfer function also, there are two poles at -1 and -2. Sorry, there are two zeros at -1 and -2. And after that, there are three poles at -2.32, -0.34, plus J0.56, and -0.34, -J0.56. If I can sketch on the S-plane, this is the location of the poles. This is the location of pole of -2.32, and this is the location of the poles -0.34 plus J0.56, and this is the last post location. Okay, so hence the system is stable because all the posts located at the left hand side of the S-plane. So you can say that this is a stable system. Okay, according to the previous example, the system is unstable. The previous example, the system is unstable. However, in this example, the system is stable. Okay, so I already prepared two exercises for you. Both of them are three order systems, third order system. So this is the question, and the question asks you to obtain the transfer function for the system below, and then you need to determine the system stability. So this is the first answer for the question number one. And then for the question number two, this is the answer. So according to this, what do you think about the system stability for the question number one? Is it stable or unstable? Just give a guess. Just try. Stable or unstable? What do you think?
Stable.
Stable, eh? So how about the question number two? Is it stable or unstable? Look at the sign. Positive, positive, and negative.
Unstable.
Unstable. Normally, if you find at the denominator part have the negative value, most probably the system become unstable. However, you can try to calculate it by using calculator lah, to see the post location. Most probably, if you have negative value there, the system is unstable. Okay, so you can say the system is stable because you can see a positive, positive, positive. All of that is positive value. All right. So that's all for the state space to transfer function. Before I proceed to the second slide, I would like to do some conclusion on this slide. Let you know that this lecture note focus on how to convert from state space to transfer function only. Okay, and then after you convert from state space to from transfer function, you can determine the stability of the system. Okay, so the most important thing that you must know based on this slide, you must know how to convert from time domain to frequency domain. You must know how to generate this formula. That's the first thing. And then the second thing, that most important part, that you must know how to use this formula in order to solve the question. Okay, you must know how to use this formula in order to obtain the transfer function based on the state space. Okay, do you have any question regarding to this? If not, I will proceed with the second slide. Just give you a brief introduction. And after that, we will continue on next week. On next Monday, Perlis is not holiday. Only the Penang is holiday, is it? Penang take holiday for New Year, is it? Penang will have public holiday on Monday.
Yes, sir.
And then PSDC will be closing too, is it?
Yes, sir.
Okay, so do you have any plan on Monday?
Same on Wednesday.
Okay, so we will do class on Wednesday, online class for the next week. Okay, all right. So next week we'll continue on Wednesday at 3 p.m. as usual. Okay, so I will go to the second slide. I need to save this one.
So
Mm-hmm.
next week is online or face to face?
Online.
Online, okay.
Okay. And after that will be face to face. Okay. So only next week will be online. Alright.
So is it still
Okay,
the
so
same
now
plan that,
you know how to. Once again,
I'm sorry to interrupt, but I'm just need to
can you ask
confirm
me
one more
again
time. Is it still the same? Hello?
the question? Can you
Hello,
please
sir?
repeat the question?
Hello, sir? Can you hear me? Hello? Hello?
Hello,
Hello?
yep. Can
Hello?
you?
Hello, sir? Can you hear me?
Uh,
Hello, sir? Can you hear me?
I can hear you. I can hear you.
Okay, okay. So
Oh
I repeat
no,
my
the
question.
internet. I can hear you. Hello.
Hello, sir? Can you hear me?
Yes, I can hear you.
Oh, okay, okay. So I think it's a big lag. So never mind, I just repeat my question. So is it still go as planned, like
Okay.
next year, which means January 2023, our control class will be on Wednesday or Monday and Wednesday?
Okay. Uh, only next week. The control class will be on Wednesday online. After
Okay,
that,
sir.
we will we will continue as usual on Monday face to face.
Okay, sir. Noted.
All right. All right.
But sir, I thought that we after
Okay.
the New Year we are on Wednesday face to face because I remember the Chinese New Year are also on Monday too.
Because I'm not happy with the evening Wednesday class. Be- because you have class on morning, on the morning, and then after that, when continue with my class, I can see you are not interested. Because I can see you don't have any focus when I do class on, you know, Wednesday evening. So that's why. For the face to face, I prefer to have Monday morning class.
So for the Chinese New Year, the also change to Wednesday online, right?
Yes, the Chinese
Okay.
New Year will be uh, online on Wednesday. All right. This semester is quite tough because there's so many holiday on Monday. Oh my God. Okay, so we just continue lah. We try to finish as soon as possible. For why I explained to you the previous slide, because the previous slide is really important in order for you to do the pole placement control design. Without the previous knowledge, you cannot do the pole placement control design. So that's why you need to learn how to convert from state space to transfer function in order for you to do this control design. Okay, so in this chapter, the student will learn about the conditions before the pole placement controller can be applied to the system. Okay, so this is the system, and then this is the output. This is block diagram, control output, and then this is the input. This is open loop, and then we can improve this system performance by adding a feedback. So now before this, from open loop become the closed loop system. Okay, so now from open loop we already improved the system by make it closed loop by adding the sensor at the feedback. So we also can make improvement by adding a controller to the system. System, we have feedback, we have the input, you have the output. So it means that in this case, you do two times of improvement. From open loop, you make it closed loop to improve the system. And then the closed loop system, you also can more improve by adding the controller to the system. So that's why we have the controller system. Okay. So in control number one, you learn about the PID controller. Okay. However, in control number two, you will learn pole placement controller. So in control number two, you will learn pole placement controller. This is the location you put the controller, pole placement controller. So that's why in this chapter, you will learn the condition before the pole placement controller can be applied to the system. So it means that if you have the system, you cannot straight away apply the pole placement. No, you cannot do that. So you need to check, is it the system is compatible with the pole placement controller or not? If compatible, you can apply the pole placement. If not compatible, you cannot apply the pole placement controller. Okay, so that's the first thing. The second thing, you will learn how to do the step to implement the controller to the system lah. Okay, so today I just want to focus number one only. So next week we will continue with the number two. All right, so example, this is system, and then this is what you learned before. You do the modeling, and then you this is in your test. Is it? In your test, you do the modeling and you obtain the transfer function. Oh, sorry, you obtain the state space. Okay, and then after that you do the analysis, stable, unstable, and so on. Okay, the the output graph, how is it, and so on. So this is everything covered in the test number one. And then Dr. Halim already explained to you state space form in parallel form, observable form, etc. So now try to focus on this thing. Controller implementation, pole placement controller and observable controller. There are two types of the controller. However, in this course, I just will focus on the pole placement controller only. Okay, so you can see that this is a system, original system. So this is x dot, this is y. If you still remember, x dot equal to ax, x dot equal to ax plus bu, y equal to cx plus du. So if you change these two equations to the signal flow graph, this is signal flow graph. Signal flow graph, this is the thing lah. X dot equal to a multiply with the x. A multiply with x plus with b multiplied with the u. So that's why become x dot equal to ax plus with bu, is it? And then y here, y equal to c multiply with the x. C multiply with the x plus with d multiply with u. Because d equal to 0, so that's why only this line. Actually, this is the signal flow graph for the state space equation lah. Alright. Okay. So, how you want to apply the pole placement controller? This is the original one. State space. This is referred to x dot equal to ax plus bu and y equal to cx plus with du. Okay. So, actually this is referred to the pole placement controller. Pole placement. Pole placement controller lah. Okay, so now the only thing, in order to apply the pole placement controller, you need to find what is the k value. K equal to what? That's your duty. So let's say the question is, please design the pole placement for this system. So your target, you only want to know what is the k value. That's all. If you know the k value, then you know how to apply the pole placement controller to the system. Easy and you just need to find the k value only. To design this controller, we just need to obtain the k values only. That's all. All right. Okay. So example number 1. Convert the system to signal flow graph, then apply the pole placement controller to the signal flow graph. Okay. So convert the system to phase variable form. Apa saya punya sini? Ni dia ni bukan. Okay. So we just go to what is the use of the pole placement controller? To stabilize an unstable system by manipulating the pole's location, and also the second use of the pole placement controller to improve the transient response to the desired design system. Okay, so there are two. So reminder, you have to use an additional controller if you want to eliminate the output error if required, such as filing. Okay, this one no need to remember lah. Okay, so this only the thing that I would like to focus on. The first is condition lah. The condition before the pole placement controller can be applied to the system. Firstly, you must make sure the system must in phase variable form. And then the second condition, the system must be controllable. Okay. So let's say if the question say that please design the pole placement controller to the system. After you do the calculation, you get the system is uncontrollable. If the system is uncontrollable, you can say that pole placement controller cannot be applied to the system. That's all. Just stop there. Okay. Let's say the second example that if you calculate the system is controllable, then you can say that the pole placement can be applied to the system. So I can put it here something like this. Reminder, pole placement controller only can be applied if and only if these conditions are fulfilled. Okay, just please bear with the reminder notes here. There are two reminder. You have to use an additional controller if you want to eliminate the output error. And then you only pole placement controller only can be applied if and only if these conditions are fulfilled. Okay, so example, check whether the system can use the pole placement controller. So this question, I just want to check the conditions only. Conditions only. That's all. Okay. So firstly, you need to convert the system to the phase variable form. You have the transfer function, and there you need to convert the system to the phase variable form. You need to refer to Dr. Halim slide, how you manage to convert from this state space, this transfer function to the phase variable form. If you need to know how to do it, I will explain to you by next week. Okay. And then step number 2, you need to check the system controllability to fulfill this condition. So you need to find the determinant value of C matrix. The C matrix, you need to use this formula B, AB, A square B. If this determinant is not equal to 0, then the system is controllable. Okay. So I give you example. B matrix is here 0, 0, 0, 1. AB is mean that matrix A need to multiply with the matrix B. So this is the answer AB. And then you need to calculate A square B. A square B actually matrix A multiply with the matrix AB. This is matrix A. And this is the result of AB. So this is the matrix AB. A, B. This is A, B. So this is the answer. Here. I just give you a brief. However, next week I will go detail by detail. Okay. So this example, how you want to check the system controllability. Let's say the system is the second order system. You need to use this formula B and AB. Okay. If the system is third order system, you need to use this formula. Okay. So let's say the system is fourth order system. You need to use this formula. Okay. So if you can imagine if fifth order system, so you can know, you can see the pattern, right? The formula. Okay, since this is a third order system, so that's why I use this formula in order to determine the controllability of the system. Okay. According to this one, finally the B, AB in A square B. B is a 0, 0, 1. AB is 0, 1, negative 5 here. And A square B is 1, negative 1, negative 5, negative 21. So I rearrange here, and then I use 2T techniques. 2T techniques. I choose one row. In this case, I choose this one. 0, 0, 1. And then I do close. Close. Because this multiply with this 0, I don't care. And then I close this one. Because multiply with 0, I don't care. I close number 1 here. So I just make it 0, 1, 1, negative 5. Okay. And then after that, I apply the sign. Positive, negative, positive. And finally, I get the answer is, I use this pattern. If still remember, 1 multiply with this is 1 here. 1. So 0 multiplied with -5 minus 1 multiplied with 1 by using this pattern. Finally, I get, what is the answer? -1. -1. So because this value is not equal to 0, thus the system is controllable because fulfill this condition. So the pole placement controller can be used in the system. So in this case, I use the 2T technique to determine the terminal. So I also explain here how to apply the 2T techniques, so you can get how to get the result, the answer. All right. So I think that's all from me. Do you have any question? I will wait another 5 minutes. So let's say if you don't have any question, you can left the meeting. Thank you so much. See you on next Wednesday and finish the pole placement controller slide. All right. So thank you so much. So anything, I will wait another 5 minutes. Okay. Bye bye.